All right. Hello, my name is Nicholas Benjamin G. Abbott, and today I will be proposing my thesis topic, which is the analysis of the symmetries of partitions of the affine space AGN, 2 into complete and maximal caps. But first, I will introduce a game. The card game Even Quads was published by the Association of Women in Mathematics in 2021, based on the work of Dr. Lauren Rose and student Jeffrey Pereira. It is The cards are of this form, which such that each card has the properties of shape, color, and number. The number ranges from 1 to 4. The possible shapes in our representation are circle, square, triangle, and star, and the possible colors are red, green, blue, and purple. Every possible combination of these properties is represented uniquely for a total of a 64 card deck. The basic rules are to look for special sets of cards called quads. In this case, for each property, you want to check that either all the cards are the same, they're all different, or they come in two pairs. For example, in this collection of cards, we have a quad because, in this case, all the shapes are the same, they're all stars. Each color is represented by some cards, so they're all different, red, green, blue, and purple. And lastly, there are two numbers for the cards. There's cards that have 2 stars and 2 cards that have 3 stars. And here we have a larger sample, and in this case, the first four the first four rows form quads, while the last two do not. In this case, the fifth row fails because the colors fail the criteria. There's 3 colors with two of one and one of each of the other, which does not follow the rules. In this case, the last row fails because both the shape and the number fail the rules. While in both cases, there's 2 shapes and 2 numbers, they're not distributed evenly. So there's only one card that has 2 shapes, while the rest have 1 shape. That fails the criteria for a quad. However, note that there are a lot of combinations still available. For example, there's the set here, which has all have 3 stars, but then in different colors. And then in natural gameplay, the dealer starts by drawing 8 cards, and then in real time, the players may call out if they can find a quad and collect those cards for themselves. This the dealer then replenishes the laid out set, and it repeats until either the deck runs out or there's no more quads on the table. Now, the question that might come up is, what if when the dealer first sets out the cards, there are no quads available? There is in fact a rule for this, as the dealer is then allowed to, if all players agree there are no quads, to add cards to the table. In this case, we find that in fact it is in fact possible that the first 8 cards does not contain a quad. In fact, 9 cards may not contain a quad. However, 10 cards does guarantee a quad. Shown on screen, we have a collection of 9 cards that contain no quads. Now, in order to convert this into a mathematical representation, we can represent each card as a string of six zeros or ones. This is a representation taken from Krieger et al., and in this case, each property corresponds to 2 of the bits. The first 2 bits correspond to the number, in this case, 2 squares. Second 2 bits correspond to the color, and the third 2 bits correspond to the shape. In this case, the sets of cards that are called quads correspond. Now, this deck corresponds to a mathematical structure called AG6, 2, an affine space where it's 6-dimensional, and because the strings are 6 digits long, and 2 because there are 2 choices of digits. Here, the sets of cards that are quads are called 2 flats. And in this case, a set of 4 points in the affine space is a 2 flat if the entry-wise sum is all even. This is the justification for our choice of representation. Effectively, this is what makes the representation a nice choice. Then the sets of cards that contain no quads, effectively the sets of points that contain no 2 flats, are called 2 caps. Here is a representation of the set of 9 cards shown before. Note that we are able to generalize this in that we don't need it necessarily to have what's it called, a 6-digit string. We are allowed to have a 4-digit string as shown here, and here is a grid representation of the affine space AG4, 2. In this case, the part highlighted in blue is a 2 flat, while the part highlighted in green is a 2 cap. So that begs an open question. Given a particular n, what is the largest possible size of a 2 cap in AGN, 2? Our current known bounds are actually not that much. We only know the values for n from 1 up to 6 for the exact value. Meanwhile, in terms of asymptotically bounding it, we've only been able to achieve what's it called? An exponential bound from above and below. Now, this problem is a generalization of what's known as the cap problem in AGN, 3, where instead of looking at strings of zeros and ones, we're looking at strings of zeros, ones, and twos, and instead of looking at quadruples of points that sum to even, we're looking at triples of points that sum to multiples of 3. Notably, this is also an unsolved problem, and it similarly has only a few known exact values with exponential bounds, as seen here. And notably, that particular problem is also best popularized by a card game called Set, published by Marcia Falco. Now, within the space of this problem and its generalizations, one novel method applied to the original cap problem is to consider partitions of the whole affine space using said maximal caps, maximal being those caps that are of largest size. For example, here we have a picture of a partition of AG4, 3 using maximal caps of size 20. This was done by Awan et al., and it revealed some interesting symmetry structures, which may have implications for the sizes in higher dimensions. Thus, the problem statement for this thesis is to analyze the complete and maximal caps, 2 caps in the affine space AGN, 2 by deriving the properties and symmetries of the partitions of AGN, 2 that use those maximal and complete 2 caps. An example presented here is a partition of AG4, 2 into two caps, the blue set and the green set, both a size 6, and 2 flat. And this structure reveals some interesting properties of the 2 caps. Next, we move on to the preliminary concepts that need to be considered in order to understand this topic. First of all, in order to simplify the understanding of why we're using zeros and ones, we will introduce the concept of a field. A field is effectively a set of objects and 2 operations that behave like addition and multiplication over the rational numbers. This means that addition and multiplication are commutative, associative, and multiplication distributes over addition, and each of them has an identity, that is a 0 and a 1, and they're invertible. That is, it's well defined to take subtraction and division of anything that's not 0. In our case, the particular field that we will be considering is the finite field F2, where the only elements are 0 and 1, and addition and multiplication are given as above. Note that this means that if there's an odd number of ones, the sum is 1, while if there's an even number, it's 0. Effectively, this means that the mentioned condition before about a vector summing to an even vector is effectively now reduced to simply a vector that sums to 0, which is easy to work with. Note that in this case, the sum of any two equal elements is 0, any element is its own additive inverse, and the square of an element is itself. These are useful properties that will simplify much of the computation. Next, we consider a vector space. A vector space is a collection of points that behave somewhat like translations in Euclidean space. That is, you can add them together in a commutative and associative way with an identity and inverse, as seen here with an example. And you can scale in some sense, though in the case of vector spaces over the field F2, the scaling is relatively trivial, since you're either multiplying by 0 or you're multiplying by 1, which doesn't change anything. Here we find that this strings of length n of elements in F2 do form a vector space. Here we have F2 to the 4 with the elements arranged in a grid pattern. An important property of a vector space is that some subsets of them also behave like vector spaces under the operations. That is, they're closed and they follow the same axioms. In this case, the set highlighted in blue is also a vector space under the same operations. Thus, we call it a subspace, in this case, three-dimensional, since you could simplify it to have only three coordinates. Next, we move on to an affine space, which is similar to a vector space, except that the origin has a diminished role in that we do not consider it as special. Effectively, we consider it a set of points where you can define a difference or a translation between points in terms of the elements of a vector space. Fortunately, it also makes sense to label these points with the elements of a vector space in themselves. Thus, the bit strings of length 4 can also form an affine space. In that case, subsets of affine spaces that also behave like affine spaces are called K-flats, where K is the dimension of the corresponding vector space. For example, we have a 3 flat in blue, a 2 flat in green, and a 1 flat in orange. Now, we find that now I reveal here that the reason why we've chosen this grid representation of the affine spaces is that it allows the finding of what's called two flats, namely these types of sets in green, to become much easier due to the fact that the rule for whether a set of points in this representation forms a two flat is effectively equivalent to the rule of whether a set of cards forms a quad. In this case, if you assign this grid to correspond to this grid, which is fairly organized with shapes corresponding to row and shapes corresponding to column and color corresponding to row, then we find it's exactly what we expect. A set of 4 points is a two flat exactly when it occupies either one column, two columns in two pairs, or all 4 columns, or it occupies either one row, 2 rows in 2 pairs, or all 4 rows. This justifies the choice of representation as it makes it a lot easier to determine from a glance whether a set of points is a two flat. And as mentioned before, a 2 cap is a collection of points that contains no 2 flat as a subset. Now, moving on to considering some of the symmetries that we care about. The symmetries that we are going to consider are transformations of the affine space called affine transformations. Effectively, these are taking the labeling as a vector space and performing first a linear transformation, that is, a transformation that preserves the sum operations of the vector space, and then an additional sum or translation of the entire space by a single vector. In our case, considering how these transformations look on our grid representation, these transformations include, but are not limited to, swapping of rows, swapping of columns, and also for example, flipping across the diagonal. Next, to organize our study of these transformations, we will consider the abstract structures called groups. Now, a group is a set with a single operation that is closed, associative, has an identity, and has inverses. For example, this multiplication table here gives this set of 6 elements a group structure. Similarly, the highlighted in blue subtable gives that set of 3 elements a group structure. So this set of 3 elements is a subgroup of this group. A particular object that is very useful in groups is a permutation. That is, a function from a set to itself that maps every element 1 to 1. That means that it's invertible. For example, here, the permutation takes 1 to 2, 2 to 3, 3 to 1, and 4 back to itself. And thus its inverse takes 2 to 1, 3 to 2, 1 to 3, and 4 again back to itself. The set of all permutations of a given set X is called the symmetric group SX. And if this set is the set of numbers from 1 to n, we call this permutation group Sn. Other examples of groups include the elements of a vector space with operation vector addition, the set of invertible linear transformations of a vector space to itself, called the general linear group, and the set of also the set of invertible affine transformations of an affine space to itself, called the affine group. Other smaller examples of groups include the cyclic group N, the cyclic group of order N, which is the set of these elements from 0 to n minus 1 using addition modulo n, that is, taking remainder mod n. And similarly, multiplication mod p of the set of elements from 1 to p minus 1, that is, multiplication but taking remainder p. This is called either the multiplicative group of the field f sub p, or it's the group of units mod p. Multiplicative group. Next, we consider special functions between groups, since these allow us to construct bigger groups or analyze their structure. Now, a homomorphism is a mapping from one group to the other such that the function preserves the group operation. That is, effectively, f of x times y is equal to f of x times f of y. One example is given here, mapping from the cyclic group of order 4 to the cyclic group of order 2, where the function is defined by simply taking the element mod 2. In this case, the image of 3 is 3 mod 2 is equal to 1, which is an element of C2. Now, the kernel of a homomorphism is defined as the set of elements in the domain that map to the identity in the codomain. In this case, the kernel of f is 0 and 2, since both of these map to 0 mod 2. Next, a special type of homomorphism is called an isomorphism. This is when an homomorphism is bijective and invertible. That is, it maps 1 to 1. If two groups have an isomorphism between them, they have effectively identical structures and are called isomorphic, which is notated like this. For example, the cyclic group of order 2 and the multiplicative group order 3 and multiplicative group mod 3 are isomorphic. They have two elements and they have the same multiplication table. The last special homomorphism to consider is an automorphism. An automorphism of a group is a permutation of the elements of the group that preserves the group element. For example, if we consider the cyclic group C3, swapping the elements 1 and 2 actually preserves the group operation. That is, 2 plus 2 equals 1, swap 1 and 2, 1 plus 1 equals 2, and that still follows the group operation. Another example of an automorphism group is that if one considers the group of a vector space considered over vector addition, then its automorphism group is simply the general linear group of that vector space. Next, we will consider some group products, which are ways to construct larger groups from smaller groups, which will allow us to describe the structure of some of the groups we consider in this paper. Now, the direct product is to take the element, to create the Cartesian product first of the element set of the groups, that is, the set of ordered pairs g comma h with g and g and h and h, and then define the group operation simply coordinate-wise, that is, g comma h times g prime comma h prime is simply g times g prime comma h times h prime. For example, given the direct product of the cyclic group of order 3 with itself, 0 comma 2 plus 1 comma 2 is equal to 0 plus 1 comma 2 plus 2, which is 1 comma 1. Next, we have a slightly more complicated group product called the semi-direct product. Given groups G and H, and a homomorphism from H to the automorphism group of G, we define the semi-direct product of G and H with respect to F as, again, over the Cartesian product. But now, instead of simply multiplying coordinate-wise, for the first coordinate, we consider the corresponding homomorphism. We consider the corresponding automorphism of the second coordinate H and apply it to the second operand G prime before multiplying it with the element G. This causes the resulting group, for example, the semi-direct product of C3 with C2, since we've mentioned that there's a homomorphism to its automorphism group. This causes the resulting group to be non-abelian, that is, non-commutative, in the case where the homomorphism from the second factor to the automorphism group is non-trivial. Some other notable examples of these kinds of products is that the additive group of a vector space is isomorphic to the product of the additive to the direct products of the additive group of its field with itself. In this case, for a prime field, that means that it's a direct product of cyclic groups of prime order. Meanwhile, the affine group of affine transformations of an affine space to itself is equal to the semi-direct product of the additive group of the vector space with the general linear group, with the general linear group being the one that's acting on the vectors. Lastly, we'll consider group actions, which is how we are considering the symmetries of how we are considering the affine transformation as symmetries acting on our sets, namely caps. Here, a group action is a homomorphism from a group to the symmetric group of a set Sx, where when considering the image of the permutation corresponding to an element G of an element of the set X, we denote it G dot X. For example, if our group is the cyclic group of order 2 and our set X is the set of numbers 0, 1, 2, and 3, where our group action is defined by G dot X is equal to X plus 2G mod 4, for example, 1 dot 1 would be 1 plus 2 times 1, which is 1 plus 2, which is equal to 3 mod 4. We call this group action faithful because of the fact that none of the group elements except for the identity correspond to the identity permutation. That is, the mapping this particular homomorphism is 1-to-1. And we say that this group action has orbits 0, 2, and 1, 3 because of the fact that given a particular element of a set X, for example, 0, the possible images of it under the group action are 0 and 2. Next, if we consider instead the group action of C4 on the set 0, 1 with group action G dot X equals X plus G mod 2, we find that we can call this a transitive group action due to the fact that every element can be taken to some other element using some group element. That is, there exists for every element in X uh, an element of G such that G dot X is equal to Y. In this case, since, for example, there's more than one element that sends 0 to itself, we say that the stabilizer of 0 is the set 0, 2 in the group C4. This is a subgroup. Lastly, we consider how these permutations affect partitions of a set. For example, let's consider the set X and the partition into the subsets 1, 2, and 3, and 4 and 5. Here, we have a permutation f mapping X to itself, and we say that f fixes the permutation pi because every element of the set is taken to the same block or part of the partition that it began in. All red elements get taken to red, all blue elements get taken to blue, and all black elements taken to black. Meanwhile, here, with the different permutation G, it does not quite do that. Instead, the red elements are all taken to blue elements, and blue elements all taken to red elements. However, elements that were in the same part before the mapping are in the same part after the mapping. So, instead of saying that G fixes pi, we say that it preserves pi, and that it preserves the partition or the separation and grouping of the different elements. Lastly, if we consider H, we see that it does neither of those things. 2 gets mapped to 2, which is in the red partition, but 3 gets mapped to 4, which is in the blue partition. Therefore, it broke the particular block when it mapped it to the codomain. Thus, H neither fixes nor preserves the partition called pi. Thus, I move on to some examples in AG 4, 2, where if we consider the partition of of AG 4, 2 into caps that I had mentioned before, here we have a permutation simply by reflecting across the diagonal. In this case, the blue cap is mapped to the blue cap, the green cap is again mapped to the green cap, and the orange flat is mapped to itself. Thus, this permutation fixes this partition of AG4, 2. Meanwhile, looking at the middle, we have another valid affine transformation that instead maps the blue cap to the green cap and the green cap to the blue cap while fixing the flat. Thus, this transformation preserves the permutation, but the partition, but does not fix it. Both of these are considered symmetries of this particular partition and are important to understanding the structure. Meanwhile, this transformation that involves swapping two blocks that is not a symmetry of the partition, since it neither fixes nor preserves the partition as a whole. Lastly, for one more product that can define the structure of a group, we define a Reith product, where given a group G, a group H, and a group action of H on some set X, we define the Reith product of G and H with respect to the action on X as defined as the semi-direct product of the direct product of G with itself indexed by X, that is, a direct product of n copies of G, where n is the size of X, indexed by the elements of X, semi-directed by product with H, where the homomorphism from H to the automorphism group of this acts by letting H permute the coordinates of this direct product based on its action on X. Thus, for example, if we consider the semi-direct product of C3 with C2, where C2 acts on the set X0, 1 by adding, then we get these group products. And of course, given that we are considering group actions on points, this type of product will be a common and useful way to describe the structure of those automorphism groups. Finally, moving on from the preliminaries, in summary, the objectives of this paper are to identify the affine symmetry groups of all maximal and complete caps up to dimension 6. These are the known and published ones, though there are some preprints that are chipping away at dimensions higher. Next is to classify up to equivalence all partitions that make use of maximal and complete caps of the affine space up to dimension 4. I'll note that in our case, in the paper, we are abbreviating two caps to caps so that we can better indicate the sizes of the caps within the paper. And lastly, we'll do some minor exploration with some notable examples in higher dimensions, namely dimensions 5 and 6, where currently the search space is too large to find all partitions, but it's enough to note the symmetry groups of some notable partitions, since we do know what two caps are available. The tools to be used for in this particular paper are NumPy to help assist with analyzing the affine symmetry group, since it has linear algebra capabilities with matrix representations, and the Cap Visualizer, a software originally made by Raphael Walker and was also used in the paper of Krieger et al. To describe these to help understand the structure of two caps. That's all. Thank you for watching.